Okay, hello, and welcome to the second lecture of 15, 8:30, and 6:30. Today's lecture is going to be about starting off with machine learning. And in fact, it'll cover something that probably many of you know and don't know by the name of machine learning, but just linear regression, which talk about a whole suite of tools. I think it fits into machine learning, but of course predates it by a long, long time, predates that term by a very, very long time. In particular, the outline will be we'll talk a little bit about energy first. This class is about energy, and we're not going to get into any details on actual physical energy systems yet. That'll be the second unit of the course. But since we're talking about energy and talking about power, it's good just to know those units and those basic ideas there if you haven't seen it before. I assume most people here probably have, so this will be a very, very basic review, though with kind of a fun example, hopefully. But it'll be a couple slides just talking about the definitions, etc. Then we'll talk about linear regression and why you might want to do things like that and how it kind of can let you make predictions about things that might be hard to model a priori. We'll talk about the optimization formulation of machine learning and exactly, or certain algorithms like linear regression, and exactly how you go about finding solutions to machine learning problems. And really optimization is going to be kind of a fundamental theme throughout this course about how we solve these problems. And if we have time then, we'll also talk some about different loss functions you can use for linear regression type methods and define what all that means. This one we might not get to today, but we'll get to it next lecture if not. So actually, first of all, were there any questions about anything on the website, on the lecture videos? Anyone look at them? I know there was some noise that was picking up the receiver. I'm going to receiving, right? Yeah. I'm going to try it one more time. I think the antenna wasn't extended. If it keeps up being noisy, I might just buy a new receiver. We'll try it one more time, but we'll see what we can do. That worked for? Did anyone try the videos at all? Actually, looking at them. Couple. Okay, they're there. The lecture notes also this morning, I believe, were not. They're corrupted for a while. They were okay at first, and I uploaded an update, and they were bad for a while, but they're right there again, and you can download them on the website again. Okay, any questions? All right, let's get started. This lecture, as I said, is going to be about the basics of machine learning, and really, really basic machine learning, in fact, in some sense, but powerful methods nonetheless. And as a motivating factor for this, remember, when I laid out the course outline, I said that there are certain physical modeling systems that we understand well, right? Electric power actually obeys pretty definite physical laws, and so we should use those physics to actually figure out what's going on. Some things are much harder to predict a priori with a model like this. For example, how much energy will Pittsburgh consume tomorrow? Right? It's really hard to model that in some physically based model and get a good answer there. So how do we go about getting predictions of things like this? And this motivates machine learning. Machine learning essentially is building models, or one interpretation of it is algorithms that can use data from systems. So we do have data about a lot of days, how much energy was consumed in those days. And machine learning really is about taking these kinds of data and producing models that can make these kind of predictions. We'll concretize this much more shortly, but this is the basic motivation here. There are a lot of elements that we can't write models for. How do we actually go about making predictions there? But again, just to sort of start out here, this class is about energy, so it's worth taking a quick 5-minute jaunt through definitions in energy. I presume is everyone familiar with sort of the basic units of energy here? Nod if yes. Okay. So this will be very, very quick then, but hopefully it'll be the next slide or two will be a fun little demonstration. Okay, so the energy is defined formally as the ability to do work. And that's kind of content free actually. What that means is energy really is applying force through a distance. So if I were to push this chair, not doing very well at it, but if I were to push this chair over some distance, it requires some force for me to push it, and that requires some amount of energy to do that then. The unit that we use of energy, the most common unit at least, is the joule. And that is a force of 1 Newton applied through 1 meter. So if it takes me a Newton to move this, which it probably is a little bit more, but if it did, and I moved it in a meter, that would be 1 joule of energy I just used to do that. You can expand this and write out the units, a kilogram per meter times meter squared times second over second squared. But really, these units aren't that meaningful in some sense. It's sort of hard to see the intuition from these units here. And so what really helps us be more familiar with what energy is really just examples of types of energy and kind of our experience of what energy can do. Importantly, and I think everyone knows this, but power is a rate of energy use, right? So power is energy per time. So in particular, a watt is 1 joule per 1 second. So it's a rate of expending energy. And it's important to keep those two distinct. I think everyone here is actually quite familiar with that, so we won't harp on that at all. The other thing I should mention is that a joule is kind of a comically small amount of energy. When we talk about using energy at big scales, like we do in homes and in cities. And so it's oftentimes more convenient to use different units like BTUs, which are also very small, or kilowatt hours, which is a kilowatt, so 1,000 watts times an hour, so that you're back to units of energy now. But that's a unit of energy, a kilowatt hour. And then for bigger things, gigawatt hours, or et cetera. And watts, similarly, we want to talk sometimes about kilowatts or megawatts or gigawatts. Again, these definitions aren't that really intuitive here. What's more important is all the forms that energy can take. So kind of one of the fundamental things about the first thing you learn about energy is the conservation of energy, right? Energy cannot be destroyed or created. It can only transfer to be converted from different forms, from one form to another. And energy takes many different forms. So some of the forms that we're more familiar with, maybe, are things like mechanical kinetic energy. That is, some mass moving at some velocity has energy. Right? That takes energy. Gravitational potential energy. That would be if you lift something up. The mass of that thing times force of gravity times the height you lift it, that's also energy. Thermal energy, or heat, really, which I know there's a difference between those two, but I'll use them very informally here. So for our sake, those are kind of the same thing. That has a similar formula. It's the temperature of, say, the gas times the number of molecules in that gas times, this is Boltzmann's constant there, our little k. And this is a really small number because we're talking about the energy per particle here. But this is another formula for energy. And really, this is actually just what this actually is. This is kinetic energy sort of at the microscopic scale of particles moving around. We call that thermal energy, though. And then things like electrical energy, which we'll cover a lot and really actually focus mainly on electricity in this course, which I'll motivate in a second. Also electromagnetic energy, or just light, right? Light's another form of energy. It's equal to the Planck constant times the frequency of the light. And other various forms. Chemical energy, which is actually very important. There's no good, real concise formula for this because it takes many different forms. But this is energy in bonds between molecules. Bonds between atoms in a molecule. And this can be released, converted to other forms by things like burning them, by burning materials, things like that. And then nuclear, the famous E equals mc squared. That's a lot of energy in nuclear. If you are able to fuse or fission atoms, you can release a whole lot of energy. So then this is kind of a catalog of some things. There are more forms as well. This is by no means a technical description here. Oftentimes also there's a big distinction between kinetic and potential energy that people make between these two things. And different forms of these different energies have potential forms or kinetic forms. And people sometimes use Q to describe potential energy. We're not really going to worry about all that. You probably know much more already than anything here. So we'll just quick reminder of some of these things. But what's kind of fun to think about, rather than just a catalog like this, is actually an example of energy conversion in practice. So here's a list of some ways of converting between different forms of energy. Right? This is the fundamental property of energy, is that we can convert between different forms of it. And this is a chart of some ways that can be converted from one form to another. So for example, thermal energy can be converted to mechanical energy basically by expanding. This is sort of a kind of a weird way of doing it, but basically the molecules are moving very fast. They want to kind of expand, and that can make things move by that expansion. Or we can convert chemical energy to thermal energy by burning it. Maybe a little bit better example. But rather than just sort of look at this chart too much, because certainly not everything is there, and there's a lot more arrows that can be in play here, I'll give a quick example, which is kind of one of my favorite examples for showing this kind of stuff. So I have my props here. What I'm going to do is something that's incredibly boring. It's take this device here, which you probably are familiar with, and turn it on. So this is a light bulb that's just turned on, right? So what on that chart just happened? Someone has to know. Come on. Yep, that's right. But let's go a little bit further back here. So what really happened is that a long time ago, there were some atoms in the sun, right? And they were pulled together, a lot of force, and fused together. Okay, that released heat, thermal energy. This heat got molecules moving very fast in the sun, and this created electromagnetic waves in the form of light, which traveled from the sun to the Earth. Okay? Millions of years ago this happened. They were picked up by some plants, so this light hit some plants back then. Maybe the plants were eaten by some dinosaurs or something like this. And that converted this light energy, the plants did it first, and the dinosaurs might have built upon that, to chemical energy. Okay? Then they died, the plants and animals, and had a lot of soil put on top of them and were compressed in the earth, and eventually turned to coal or some other form of fossil fuel. What we did then is we now, fast forward to the current time, we went and we dug that up, lit that coal on fire in a plant to make heat. This plant then, using this heat, we boiled some water, right? The water expanded, turned to some steam, expanded, and got some generator turbines going. These turbines then were connected to a magnet in an electrical wire. Spinning through that created electrical energy, which, as was said, traveled from the power plant down these lines to the outlet here. I put through a resistor, this light bulb, turned into thermal energy, got hot, and that created some more light. So kind of a roundabout process, right? Let me do something else now. So I'm going to replace this old light bulb here with these things that are going to save us, right? This is an LED light bulb. It costs, I bought it was $50, I think, but it's come a lot cheaper now. I'll turn this on. And this is about 5 times more efficient than that bulb, right? And what it's doing is it's cutting out a single step from this process. It is going directly, approximately, from electrical energy to electromagnetic energy. That's what an LED does, essentially, without going through heat first. So we're 5 times more efficient by cutting out a single step in this process, right? And that hopefully gives you some idea about the potential gains we could make, too, about how inefficient this process is, and also sort of how impressive the nuclear energy in the sun is, just how much we're talking about here, energy that there's being produced there. I can't, unfortunately, do it in this classroom, but what I usually do in this demo, too, is then walk over to a window and open it, and that would cut out a few more steps here, right? Because that's directly nuclear to thermal to light that we're using. That cuts out this whole big loop that we're doing here through the process. So unfortunately, this room, we don't have windows. So we are forced to go through this whole process here. And hopefully, eventually, if we use more renewables, this process will be a little bit shorter, too, where maybe we just use the thermal energy directly, or light to create electrical energy directly, say if it's solar panels, and cut out a lot of these loops here. But this is sort of the basic idea of energy, and this is sort of a fun example, too, to kind of think about how many steps things had to go through to actually make energy that we use that comes out of our electrical outlets there. All right, so let's get to sort of real stuff, the content of the course now. And the first thing I'm going to talk about is electrical consumption. So we're making the move now from energy as a whole to electricity in particular. And that's kind of an odd move, right? Because electricity actually is not all the energy we use by any means. It's kind of it's a substantial fraction, but certainly not all of it. And so why do we talk about electricity here instead of energy as a whole? And the reason is really, there are two reasons for this. One is just more practical in that we can get a lot of data about electricity. It's much harder to sort of track, for example, where every barrel of oil in the US goes to and when it's being consumed, et cetera. Whereas electricity, it's actually required that people report exactly how much electricity different zones use. And the second one is that electricity is one of the few forms of energy that's kind of very rich, right? We can accomplish almost anything we want to do, at least in theory, with electricity. Kind of a very high quality form of energy. Whereas something like heat, sort of a low quality form, right? We have to get a big temperature difference in order to have heat actually do any work on something. And then there's a lot of losses associated with converting that to electricity. And so in general, we sort of think of, well, we're going to talk about energy that can kind of do whatever we want. Electricity is a good example. And I guess also, electricity is one of the few forms that can be generated in renewable ways, right? We know how to generate electricity from wind, from solar, et cetera. You can say the same thing about some chemical energy, like with biomass, these kind of things. But this is a good example of energy that can be generated in a sustainable manner. So this plot here shows, for a couple different days in the year, I think this is from 2011, the energy consumption of the Duquesne Light service area. Duquesne is the utility that serves Pittsburgh here. It's mainly the Pittsburgh area. In fact, I have a map this next slide. So it serves Pittsburgh, a couple more areas in other counties around it. But basically, it's Pittsburgh and the Pittsburgh area. So this is the energy that we use, our energy. And this shows, for a few days in the year, which or how much energy we use by different times of day. And really, actually, it's more about the power that we're currently drawing, average over that whole hour. But you can convert this to energy because it's average power over that hour. And so, for example, on July 13th, I should actually use power because these are in units of power. It's important to know. These are talking about the average power draw, so the average rate which we used energy for this day. And it shows different hours of the day. So starting at midnight and going to the next minute the next day, what the demand of power looked like. And so it was sort of a minimum at around 4 in the morning, which makes sense because not many people are up right then. And a maximum for July 13th of, maybe 4 or 5 in the afternoon. Which also makes sense because on summer days, a lot of electricity is used for air conditioning. So we have to spend a lot of energy here to cool everything down from a hot temperature. In the winter, and here's one, and actually a little kind of similar here, but here's one from February and one from October. It looks a little bit different. The peaks aren't as high because we're not using electricity to cool things down. Now, we are using energy in the winter very often. We're using typically gas to heat buildings, but that does not show up in this electricity readings, right? Because electricity actually is actually a very inefficient way, typically, if you just put it through a resistor. That would be a pretty inefficient way to heat up a home. Instead, we usually do things like just burn gas directly at a furnace on location. So, and it kind of looks similar in general. It looks like what you would expect here, right? It's low again at the same time. Doesn't go quite as high, but it's higher during the middle of the day and then lower. This data is all available publicly online. You can get hour-by-hour readings of every day for the last many, many years of how much consumption, how much power was being drawn. Again, this is for this sort of just Duquesne Light area here, which is, it's good to sort of have a personal idea of how much we use. And we were using the order of between 1 and 2 gigawatts usually, with higher peaks in the summer. So now there's another question. Suppose I were to ask you, what will the highest demand of electricity, in the Duquesne Light utility be tomorrow? And this could be an interesting question. How do you know what's going to be like tomorrow? You don't, right? I mean, people are going to do what they're going to do. They're going to act as they want to. They can turn on a light switch if they want to. They cannot if they want to. But yet, an interesting thing is this is actually somewhat predictable, what people are going to do with their energy. For example, if we know something else about tomorrow, for example, you might imagine in my example that, that air conditioning used a lot of power, right? So it kind of makes sense then that, well, if it's a hotter day in the summer, say, we'll probably use more power than if it's a cooler day. And so we can actually predict things like this if we know other things about tomorrow. So say, for example, we knew what the temperature was going to be like tomorrow. Okay, we'll ignore the fact that that's also going to be a prediction. We'll just assume we just know what it's going to be. What we can do is we can take a whole lot, and again, it'd be hard for you to come up with sort of, oh, I know it's going to be 70 degrees today, so I just by my, innate mathematical numbers here, I'll crunch them and I'll figure out how much energy we're going to use. That's tough, but we do have a lot of data of these things. That's the key point here. So we can take a whole bunch of days. We can get historical weather information. This is from a site called Weather Underground that I usually scrape these from. And we can get historical consumption data from PJM, which I was talking about before. Right? And we can plot these now on a plot. So I should mention here, I'm only talking about peak demand. So I'm looking at this curve here. I'm looking at just the highest point. This is actually very important to know in and of itself, even if you don't know the whole thing. Just knowing the highest point is actually very important because the highest thing is kind of the most energy you have to schedule for. Right? You have to have these many plants operating maybe. Maybe it takes a while to get plants up and running, so you have to kind of plan out ahead for them to be able to meet the maximum demand here. And so I want to try to predict what this peak demand is going to be. And I'm going to do this from knowing what the high temperature is going to be. Again, if I take a bunch of points and plot them, you see kind of the expected relationship here. I should emphasize this is only for June through August. This is data from Pittsburgh and Duquesne Light from 2008 to 2011. So 4 years of data showing for every day the high temperature and the corresponding peak demand. And as we expected, the higher the high temperature is, the more we tend to use. Because this is a lot based on air conditioning and things like this. So now, what if we have a new day tomorrow, and I say, okay, I look at my forecast, and it's going to be 83 degrees tomorrow. How much energy are we going to use? Well, conceptually, a nice way of doing this, of building a model here, I mean, there's going to be some, you can't get it exactly, right? Because there's some days where the high temperature was the same, yet there was some spread of how much you get consumed. But you might get a pretty good estimate from this. And the idea actually is quite simple. You've probably seen it before in other classes. It's let's fit a line to this data. And I'll be much more specific by what I mean by that in a second. But let's just draw a line through it. When I say through it, and in some sense, this is a good line to draw through it. And now let's make our predictions based on this line. Right, so I'm going to say that my predicted peak demand for a day is going to be equal to some number, so I'm calling theta 1, times the high temperature. This is the slope of the line here, plus some number theta 2, which is the bias term, right, the offset. This is all really, really simple stuff. I'm sure you've seen this before. And for this model in particular, the slope of the line would be 0.46, and the intercept is negative 1.46. But this draws a line that goes kind of through the data. So now, if you have a new point, say, I know that the temperature is going to be 80 degrees Fahrenheit tomorrow. I can use that to make predictions, right? I can take my formula for this line, plug in 80 degrees Fahrenheit, and get a prediction of how many gigawatts will be the peak power demand tomorrow. And really what they're doing here, we're just looking at this line, going to 80, going up to this line, and saying that's about 2.2. But this sort of idea of a line like this being a model and being a prediction is just important to think about conceptually. This line here makes predictions for us in some sense. All right, so let me formalize the setting a little bit. And I'll write on the board, even though all the stuff I think I'm going to write is there, I think it's worth just emphasizing some of this, because this notation we're going to use throughout the whole class. So I'm going to use x to talk about my input. So my input is going to be denoted by numbers, or vectors, xi, which are n-dimensional vectors. So here, for example, we have one input, so n equals 1 in this simple case, because our input is just the high temperature for the day. The output, and it's also important to note, I am using this subscript here not to talk about indexing into the vector here, but actually to describe the index of the data point itself. So each xi is a vector in Rn, and I should say we have m of these. So we have m different data points, just by notation. The output, the thing we want to predict, I'm going to call yi, and that's just a real number. And the fact that it's a real number makes this what we call a regression task. If I were discrete valued, we'd call it a classification task. That's the only difference between these two things. Is regression is real predictions, classification is discrete predictions. And for this example, again, the output here would just be the peak demand for that day. And again, it would just be real valued here. We also have some things, which I use theta to denote, which are called the parameters of the model. And this is a vector theta, which is k-dimensional. And I'll be a little bit more formal in a second about how we use those parameters to make predictions. But the last thing is that the predicted output is just this quantity yi hat, which is also a real number. So this makes sense, right? I mean, we want to predict a real number. We're going to make some prediction here. For example, in our old setting, yi hat would be theta 1, that was the slope term, times our input, that was the high temperature, plus theta 2, that was our bias term. And so that's how we use the parameters to go from the input to a predicted output. Now, it's nice there's a little bit more formal notation here to talk about this mapping, right, from input to predicted output. And the way we're going to do that here is we're going to talk about features. So formally, a feature mapping, is a function, phi, which takes as input these x variables in Rn and outputs some vector in Rk. So features, or really the feature mapping, is a function phi from Rn to Rk. And it's nice to think about like this, think about it in this way, because we can actually cover a huge number of possible models by using more and more expressive features here. So in fact, we're talking about linear regression today, but we'll soon move on to nonlinear regression, and in fact, kernel-based regression. And all of that, in some sense, can be thought of as linear regression just with more expressive features. If you didn't see that before, don't worry, we'll cover that in a lot of detail. But really, a lot of what we do can be expressed using linear models, but very complex features here. Now, in this example, the features are quite simple, right? The features take as an input xi and just map it to a vector, which is both has xi as the first element and a constant term as the next element, right? Because we actually had both some input term and a constant term in our model, so our feature just has both of these here. And obviously, in this case, maybe it's not that important to do this here. You could really, it's just one feature and then one constant term. You could represent that. But these features are going to be very important to think about going forward. So now with this formulation here, we can actually write our predictions a little bit more explicitly. So we're going to say that our prediction, yi hat, is equal to the sum over all j equal from 1 to k. So that's summing over all the different features. Theta k, and here sub k means I'm indexing to the kth element. Sorry, j. I'm indexing to the jth element. Times phi j of xi. So I'm taking each feature, multiplying it by the corresponding element of theta. And we just are going to write this in the fall. It's sort of a little bit cumbersome to write out sums all the time. So we're going to write this as theta transpose phi of xi. Now, this is just a simple sort of linear algebra function here. Theta and x and phi are both vectors of size k. And if you remember from matrix multiplication, you can multiply. You can't multiply together two vectors just side by side like this, right? The different dimensions have to match up. And so what we're really doing here is we're just transposing the first one to make it a row vector. This is theta and this is phi. And then we're multiplying these two. And this is an inner product between these two vectors, which is just equal to the sum over all the different corresponding elements. Sum of the product of the corresponding elements. OK. So now I'm going to talk about something called a loss function. And a loss function encapsulates the following idea. We would like, in the ideal case, our predictions are defined in this model just as some function here, right? We're just using some parameters theta, and our predictions are some function of these things. But we kind of want these to be, in some sense, good predictions, right? Otherwise, it's just sort of silly. We're just generating kind of numbers otherwise. And so we're going to measure what kind of a good set of parameters is by means of a loss function. And what I mean by that is we just want a model that, in some sense, performs well, or where the predicted outputs are kind of close to the actual outputs. Again, for all the data in our data set here. So for all these things, I should just say this goes I equals 1 to m. So for all m of these, we want it to be close. Now maybe we can't have it be exactly equal, but we still would like it to be close. Otherwise, it's going to be a pretty bad model, right? Making these predictions that are nowhere near the true outputs. Those won't give very good predictions. And we measure closeness of the predicted output and the actual output by means of a loss function. So I'm going to define a loss function as some function L, which takes as input two real numbers and outputs a positive real number. And one of these real numbers is the predicted output, one is the actual output, and outputs some positive number, which if the number is 0, it means they're really close together. If the number is big, it means they're pretty far apart. A simple example is just what's called the squared loss, or and when you use squared loss in linear regression, it's often called least squares linear regression. But basically, we just take the difference here and we square it. So that satisfies everything, right? That's a big number when they're far away. It's small when they're equal. In fact, 0 when they're equal. It's always positive too. So that's a common loss function. So now what we want to do is we want to find some set of parameters that make this loss function small over the whole data set. Right? So we want to take all our data points, all m of them, and we're going to define the overall cost function here, which I'm going to call j of theta, as the sum of the losses for each example that we have. And in this case, if we use sort of this linear function for the predicted output, and we use the least squares loss, this would be a sum over all our data points of theta transpose phi, which is our prediction, minus the true output y, then we square it all. Everyone, people probably seen this before, I would imagine, right? Just nod if you've seen this before. All right. And we can write this formally as the problem of we have our cost function here, and we want to minimize it over theta. This is an example of an optimization problem. Okay, we have some objective, which is a function of theta, and we want to find the theta that minimizes this objective. It's a very simple optimization problem, and it's one that you probably can have seen before and know about and know how to solve. But it's very important to think about these problems in terms of optimization. And this is really going to be a theme throughout the course. And a lot of what sound like very complex machine learning methods are really no more complex than this. We just have a different loss function. That's all that's going on here. They're just optimization just like this. All right. So how do we actually go about optimizing that? How do we solve that optimization problem? And here, oops, my clicker broke. Before I do that, though, I want to define this in a little bit more, well, not concrete, but a little bit more compact notation. And again, this stuff is going to be actually very common throughout the course, too. So it's good to know how to do this kind of manipulations of vectors and matrices here. So I'm going to define some matrices and a vector. So I'm going to define big phi here as a matrix that contains features for all the m examples as the rows of this matrix. Okay, so in the first row is the feature vector for the first example, second row for the second example, etc. And remember, these feature vectors are themselves vectors, which are column vectors. So to make them rows in the matrix, we have to transpose them. Right? This is a definitional notation here. We're also going to define a big vector now of all the outputs, y's, right? Which again just has the first, and I should say this matrix here, phi, is going to be a matrix that is m by k, right? Because there's m different rows and k different columns for each feature vector. The outputs is going to be a vector in Rm. You have one item for each example you've seen. And now we can write our cost function in more compact notation. So what we can do is we can take this, which just sort of has a sum in it. You know, we tried to get rid of sums before. We're going to do it again. And we're going to say that our cost function j, which is equal to what I saw before, is now equal to j of theta now equals the 2 norm of big phi times theta minus y, 2 squared. This notation here is a 2 norm. The 2 norm is just going to be the square root of the sum of all the elements squared, equal to also the square root of z transpose z. This is for an arbitrary vector z. And so, well, all it really is it's each element here. We take it and we square it. It's the sum of all those. And if we take the squared 2 norm, that will just leave them all squared then. So what's important to see here, really, is that this term, this is a vector in Rm. Right? Because theta here, phi here is m by k. Theta is vector in Rk. When you multiply them, you get a vector in Rm. Subtract out another vector in Rm. That's going to be a vector in Rm. And actually, is it obvious to everyone that the elements of this matrix, the ith element of this matrix here, of this vector here, is just going to be equal to this term here, theta transpose times phi of xi. That's obvious to everyone? Just okay. Please ask questions. This is not obvious because this sort of notation is used sort of throughout the whole class. And we call this thing here the least squares objective function. Also called square loss, but I'll use those two kind of interchangeably. Okay, so now how do we actually go about finding the theta? Remember, this is a function now, right? This takes as input a theta, takes this and outputs a real number. right? Because norms squared are a single real number. So now we want to find the parameters theta that actually minimize this cost function. Remember, that was our objective before. Find theta that minimizes this cost function. So how do we do that? Well, let's think about the 1D case. Suppose we have some function, j of theta, where theta here is just one-dimensional. And I'll just write it. It's x squared minus 2, sorry, theta squared minus 2 theta minus 1. That looks like this little quadratic function here. The minimum, clearly you can just look at and see, is right here. And how do you find that minimum? Anyone know? Right. So the derivative is the slope of this function at every point, right? And so the function has to be at a minimum where this derivative goes is at 0, right? Because that's where it's kind of flat and couldn't go down from there. For general functions, this might just be there could be many minimum, right? Many minima. And there might be one here, then it might go off this way and have another one over there. That can be tough. For a certain class of functions, though, which we'll deal with a lot in this class, called convex functions, it turns out that there's only one global optimum. And so, there's only one local optimum, and that local optimum then is also a global optimum. But again, the way you find this, you take the derivative with respect to theta, which is 2 theta minus 2, find where it turns 0, and that's your optimum. That's your optimal theta. So the theta is where the derivative is equal to 0. And to solve it then, you just plug this formula for the derivative, set it equal to 0, and then solve for theta star. Now, that's probably everyone's seen that before. I assume probably a lot of people have seen this next thing too. But how do you do this now for a function where theta is not just a single number here, but it's actually a vector? It's a little trickier, but actually it's not any trickier at all. I did myself there. We need a little bit more notation, though. And we're going to define something called the gradient of a function. So I'm going to keep writing kind of in this one spot so that you can both zoom in high enough to see it on the video. And but it means I'm going to have to erase a lot, so hopefully that'll be OK. I'll be on video if you want to see things I've written before. So let's talk about the gradient. If we have some function j, where importantly here, j is a function that takes vectors Rn as input. Actually, I'll use Rk there because that's what I've used throughout the rest. Takes vectors in Rk as input and outputs real value numbers. Then a generalized condition for the function for theta here, theta star, minimizing that function, would be something called the gradient is all equal to 0. The gradient is just a generalization of the derivative to vector input functions that take as input vectors. And all it is very, very simple, but we're going to use this little notation, this little triangle here. The gradient with respect to theta of j of theta is just equal to a big vector of all the partial derivatives with respect to different elements of theta. So the first element is the derivative of j with respect to theta 1, then derivative of j with respect to theta 2, etc., to the derivative partial of j partial theta k. And really, this is kind of intuitive, because if you have some function that takes input a vector, in order for it to be at a minimum, it kind of has to be at a minimum with respect to all its different dimensions of that vector, right? It has to be that you can't move down in any direction, so that gradient has to be 0 with respect to every single possible input, every dimension of the input. Sorry. Now, what's important now, fortunately, this is actually the little bit of calculus we're going to use, but this is as hard as it gets here because we're really just going to do derivative calculus in this course. And one of the more important things about the gradients are some little rules and some common gradients that we might have. So we're going to use these in a second to derive the expression for that least squared solution. And the rules just are the following. First of all, the gradient is what's called a linear operator. So if you have two functions added together and maybe multiplied by some constants a and b, then the gradient of this whole thing is equal to a times gradient of the first one plus b times gradient of the second one. This is called a linear operator when you can do things like this. So if you have a sum of things, you take the gradient, you take the gradient of each one of them individually and add them up. It's the simplest example here. A little bit more specialized examples. And these are all derived in those lecture notes on linear algebra that I posted on the website. So if you want to sort of refresh yourself about why these are true, you can look at that. But they're kind of generalizations of these same types of formulas for scalar valued quantities. So if our function j of theta, I'm not sure if we can see that from here. If j of theta equals theta transpose some matrix A times theta, this is going to be a real valued number, right? Sorry, here A is a matrix in R k by k. And so this is going to be a real number, right? Because you take this k by k times a vector, that's going to be a vector in Rk. You multiply it, take the dot product of it with theta again, that's going to result in a real valued number. So this function, again, maps from vectors to real numbers. And the gradient is equal to A plus A transpose times theta. And you can do this, the way you do these things is you write them out kind of element by element. Or the easy way to do them, in some sense, is write them out element by element and kind of figure out what this partial derivative is for every single different element here. That's the way you can kind of compute these things. This is sort of looks like what this should remind you of is that for a real number, so for Rn, sorry, for theta in R, the derivative here is just equal to 2a theta. Sorry, I wrote partial there, not 2. 2a theta. Right? The derivative of theta, a times theta squared here, which is what it would be equal to 2a theta. Another very important one is that if the function, if j of theta equals b transpose theta, then the gradient of j of theta just equals b. That's actually very easy to show, so maybe I'll even show that one. So I use some space here. Sorry, it's sort of hard to cram everything into this little bit of the board here, but we'll give it a shot. So remember, b transpose theta equals the sum over all j equals 1 to k of bj times theta j. So if we take the derivative of this with respect to, say, theta, I guess I'll use theta I here, of this thing, well, theta I only comes into account here when j is equal to I. So this will equal, all the other terms will go away because they don't depend on theta I. So this will equal bi. So if the partial with respect to theta I equals bi, then the vector of all these partials will just be equal to b. So that's an easy one. This one's a little bit harder to show if you just write it out element by element, but it's not really any harder. It's essentially the same thing. You just do it element by element and see what's going on. OK, so now we have at hand our conditions here. We know the gradient has to be equal to 0. We have these rules. Let's go and solve this least squares problem. We have all our tools now to do it. OK, so I'm just going to write this out. This is, again, a very simple derivation. It's really amazingly nice in some sense. Beautiful. But it's worth going through just to make sure you understand it. And if you haven't seen it before, it's very, very good to get this sort of be familiar with this, because so many of our other derivations are going to be like this. And that is kind of, it is sort of one of the simplest possible examples. One of the few examples where you can actually come up with an analytical closed form solution for what this optimum is. But it's a very nice case for that reason. All right, so I'm going to write this again. Again, this is maybe a little bit repetitive here, but we'll soon get into a little bit more complex notations here, or more complex objectives here. But again, if you haven't seen it before, it's very, very good to be familiar with this. So our objective here, remember, was j of theta, which equals this phi times theta minus y, the 2 norms squared. Right? And this squared 2 norm is just equal to this thing transposed times itself. Right? So that just equals phi theta minus y transpose phi theta minus y. Now let's just write this out, distribute this out, this product out. We can do that with matrices. They do, in fact, obey the associative property. The right one? Yeah. So we can write this out term by term here. And this just equals, now just multiplying these two terms, theta transpose phi theta minus 2, this one times that one. Or so you have one term that's that times that, and you have one term that's that times that. But these are just the transposes of each other, so they end up being the same. So this is equal to 2y transpose phi theta. Did everyone follow that step, actually? Why this is the 2 that comes up there? OK. If not, maybe I'll just write it out. So we have one of these terms, and you also have minus theta transpose phi transpose y. But this term is just a real valued number. You can take its transpose. The transpose just flips, flips this around and flips which things have transpose and which don't. That equals the same thing as that. So you just simply have 2 of these terms here. And then plus the last one here. There's negative on both of these things, so it ends up being positive, plus y transpose y. OK, this is written out term by term now. Now let's take this gradient. Let's find what the gradient of this thing is. And to do that, this is going to be the gradient of this expression we've written out here. And now we're going to apply this linearity property, right? Where if we have the gradient of a sum, we can push that gradient within all the terms of the sum. And if we have a constant here, we can just push that constant outside the gradient. This is going to be equal to the gradient with theta of theta transpose phi theta minus 2 times the gradient of y transpose phi theta minus the gradient, or plus the gradient of this last thing, the theta of y transpose y. Now let's apply our rules from the last slide to simplify this even more. So if you remember, this first term looks like that quadratic form we saw in the last time, right? So that's this rule here we can apply. The derivative of the gradient with theta of theta transpose a theta is this thing. So that's equal to, this one is equal to phi transpose phi plus phi transpose, which I'll just write out like that for now. But this is symmetric, this matrix, so it's equal to its transpose. So really you just have 2 of these things. 2 phi transpose phi times theta. This one here is really just like, well, it's sort of like this thing. Let's write it here, actually. It's minus 2. This is sort of like B transpose here, right, in our rule that we're applying. And so this is minus 2. It's really this thing transpose, so it's phi transpose y. And then this thing doesn't depend on theta at all, so it's nothing. Now, to solve it, remember, we set this equal to 0. So we're going to set this to be equal to 0. And I'll just to make sure clear what we're doing here, I'm only doing this when I say that the optimal theta is such that this is equal to 0. And now we just solve it, right? Now we can move this over to that side and say that, and also divide by 2 and say that's theta transpose theta phi equals theta transpose y, or finally theta star equals phi transpose, sorry, I'm getting a little sloppy down here, equals phi transpose phi inverse phi transpose y. Now this is probably the single most, or one of the single most used expressions in data, all of data analysis, right? People run linear regression so much that it becomes almost second nature. So, in fact, it's so common there's a special name for this. This is known as the normal equations. So this solution here are really, I mean, these equations here are called the normal equations. All right, so let's see how you actually do this now, going from math to MATLAB. A big part of this course, as I said, is going to be taking kind of mathematical descriptions and writing the code for them. So this is actually a pretty simple operation to do in MATLAB. And even though other things look harder, they also can be quite simple themselves. And so we're going to use MATLAB extensively throughout this course to kind of actually solve these type of problems. Let's make sure what time it is, see how we're doing. OK. All right, so here's some MATLAB code that would solve the least squares problem for that, for actually quite a little bit of a different problem here, but some different parameters here, but it's for a temperature problem like we saw before. Actually, I should fix this just putting in the official ones for our data that we're using here. But essentially, what this does is the first line loads a text file that has a list of all those high temperatures in it. Right? So each line of that file will be a high temperature for a day. And this next file, peakdemand.txt, is going to be a file that has peak demands for each day, corresponding to the same, so the lines correspond to each other in the two files. This just populates each of these with a big vector of these things and a vector of those things. Now, just for notation, I'm going to let n be the size of x. That was our definition, remember? We said n was the size of the input. M is a number of examples, so that's the number of rows in that matrix X there. Now I'm going to construct my feature matrix. Remember, this is a matrix that contains all the feature vectors. And that is equal to a matrix whose first column is this vector of x's, and whose next column is a vector of 1s. Remember, phi here, the way we defined it, it was a matrix that had phi of x1 transpose in the first row. And so in our example, phi here, for this simple linear regression task, is just going to be the example and then a constant term. So thinking about it in terms of a matrix now, the first row of this matrix, sorry, the first column of this matrix would be the x's, second column would be 1s. That's how we construct it here. And then we can write theta equals, just plug in our solution here, phi transpose phi, inverse of that times phi transpose times y. The little tick here in MATLAB means transposes. And the inv function computes the inverse of a matrix. Now, in fact, this is so common that MATLAB has a special operation for this, which is one character. It's the backslash. You compute this exact same thing by just typing phi backslash y. That computes the least squares solution too. And I should say, this will give you the theta here. This is for slightly different data, but I'll put in the data the correct values for our example, which was like 0.046 and then negative 1.46, something like that. OK, so does everyone sort of get the mapping between these two things? It's pretty simple here, certainly. But in general, it's good to know, and actually a really important point is to be able to go from optimization problems to these kind of actual code that will solve it. Yeah?
Is this least square loss function kind of similar to projection?
Yeah, absolutely. So there's a lot of ways of deriving least squares. One way is by this loss function, right? Another way is it's the thing that if you project these data points to a line, it minimizes the distance of this projection in some sense. So there's a lot of ways of thinking about how least squares work. Or least squares can be the projection of all the data onto a one-dimensional, in this case, line. So there's lots of ways of describing least squares. You can derive this same kind of formula in a lot of different ways. The reason I'm writing it this way is because a lot of what we do is framed as optimization problems. And it's easy now to think of it, at least conceptually, saying, well, and we'll get to this, I think we'll probably do it next time, but we'll get to it and say, what if you were to use not this squared error, but some other loss function? How would that change your method? And if you're just looking about sort of in terms of projections, it's not really that clear. It's like, how does this actually change the problem? What changes about it, et cetera? So I really like the optimization formulation of these methods. But yeah, absolutely. Least squares is also a projection onto a line. So yeah, those things definitely work. OK, so as a little aside, this was sort of a very hopefully gentle introduction to what we're generally calling optimization problems. This is a case where you just had an objective function and want to minimize it. But in general, you can have much, much more than that. So in general, we might want to solve some problem where we minimize some function j of theta, subject to a bunch more constraints on it. Say, for example, we had constraints that maybe the high temperature, the peak demand, couldn't possibly be over a certain amount. We just know that. Or the high temperature of a day couldn't possibly be over a certain amount. So there might be other constraints we want to impose on this estimation problem too. Maybe we want to sort of clip the maximum values of theta because we know the slope couldn't possibly be that much. And we're going to formulate these in general as minimizing some function subject to a bunch of functions g of theta being less than 0, and a bunch of functions h of theta being equal to 0. This is sort of a general formulation of a constrained optimization problem, because we add these constraints on what we can have as our allowable values. And this is a pretty general formulation, but really specializations of this cover a huge range of possible optimization problems. So things like, if you've seen before, linear programming, quadratic programming, semi-definite programming, or even integer programming, they're all examples of this kind of formulation. And so it's very good to have this kind of generic formulation in mind when we start writing these problems. Now, an important, very, very important distinction here, which will be important to this class, is that of convexity. So how many people have seen convexity before, just by a show of hands? OK, so maybe a third or so. So we're not going to get too formal into it, because you can get kind of arbitrarily complex when you start talking about convexity. But the basic idea is very, very simple. Convex functions, you can think of kind of like bowl-shaped functions. So a convex function the formal definition is, if you take any 2 points of this function and draw a line between them, that line will lie above the function itself. Now, why is that sort of important? Well, a very, very simple proof will show that convex functions, don't worry about the constraints for now, but convex functions have one local optima, which is a global optima. And actually, I should be a little bit careful here, because they may have many local optima that could be non-unique. There could be all sorts of boundary cases that things are not, not quite like that. So I should probably take that back. But maybe say it a little differently. The local optima of a convex function are also global optima. And what this means is, if you sort of search around for any place that has a gradient of 0, you will have found the global optimum of that function, or a global optima of that function. So you won't be able to find, no matter how much you search, any parameters theta that do any better than that. And very informally speaking, what this means practically is that we can develop algorithms that are able to find these things, find these optima, very, very reliably and very efficiently. So these are good problems for people that like to solve problems efficiently and like to get answers back quickly. Now, the last thing I'm going to talk about today, I think, is how we actually go about solving these. So hopefully, probably a lot of you have seen a lot of this material before. If you haven't seen this before, this is going to be a very, very cool thing that we'll go over in this class a lot. So convexity has been known for a long time. It's been known for a long time that these problems are in some sense easy to solve, at least in theory. And so if we formulate our prediction problem, we want to predict something about energy, we formulate that as a convex problem, that should be easy to solve then. But what's emerged recently in the past 10 years or so, or maybe even more recently than that, maybe the past 5 or 6 years, has been a variety of generic optimization libraries that can make it very, very easy to solve these problems. And we'll get into tomorrow, or next week, I should say, about just so it's showing an example of just how much easier it is to solve, in some cases, using one of these generic solvers. But the one we're going to use throughout this course is called YALMIP. YALMIP stands for Yet Another Linear Matrix Inequality Parser. That name is a little bit antiquated at this point, because it does much more than that at this point. But essentially what YALMIP lets you do is it lets you write optimization problems in a very intuitive and descriptive form. Where you remember that to solve the least squares problem, we have to go through that derivation of, OK, here's the gradient, set it equal to 0, let's solve for that. What YALMIP lets you do is just write the optimization problem kind of in a natural form. Just write out the objective, and it will solve it. So here's an example of this least squares problem solved with YALMIP. And again, I have the wrong answers here, but I'll fix those in the slides. Take all your same data as before. Remember, we had this x or phi and y matrices here. Take them all as before, and then run the following code in MATLAB. Some things here are just kind of notational. You have to they're just a call to this YALMIP library, which you have to just get used to. And one of those is defining variables of optimization. So this function SDPVAR defines an optimization variable. And SDP, if you're interested, stands for semi-definite program. YALMIP was first designed to handle this very general class of problems called semi-definite programs, but it can solve much easier ones too than this. So the name of the function is just SDPVAR. That creates, it's supposed to be k here, sorry. This should be a k by 1 dimensional vector. Yeah?
Is there any reason why we're using YALMIP as opposed to any other optimization?
So you mean as opposed to which ones?
CVX.
So CVX and YALMIP are essentially equivalent for convex problems. YALMIP's a little bit nicer in some ways because it can handle non-convex problems as well to a certain extent, which we'll deal with a little bit here, like integer problems. And it also has, as a backend, a lot more different kinds of solvers. So YALMIP can use, say, for example, CPLEX, which is a very fast linear programming, quadratic programming solver at its backend. I use CVX plenty as well. I've actually used that maybe even a little more often in my own work. But those two are both very good. the other ones that are out there typically are much kind of less intuitive to use. So CVX and YAML are two examples of these very intuitive generic libraries for optimization. If you know CVX already, it actually is good to learn YAML too, because they're a little bit different in their capabilities there. And the fact that you can use a lot of different solvers can really help you sometimes. So for example, Cplex has very good mixed integer programming solvers. And so we're going to be able to use those if we want to instill a quick formulation like this, which you can't do in CVX. I like CVX actually, some sense of notation a lot as well, but that's sort of a personal decision. But we're going to use YAML here for those reasons. Yeah?
So this is an open source.
Yes, it is open source. The killer here is that MATLAB is not open source. And these are all, CVX and YAML are both based in MATLAB. And in fact, they don't have good ports to any other language, which is really, really too bad. There are efforts underway to make Python things like this that would work as well. MATLAB's free for us here, but that doesn't really help people that aren't at CMU, so or not at the university that can do that. But
You also mentioned Cplex. That's another.
Cplex also, yes, Cplex is also.
You don't have access to that.
Oh, no, Cplex for academic use is free. You can download it from IBM's site.
Really?
Yeah. So again, we can use that here, but yes, you can't. It's not. That's definitely not open source, and if you're not an academic, they will charge you a lot for that. So it's sort of too bad. There are a lot of solvers that work with YAML that are free, and we'll be using those primarily. It's mainly if you want to go on and have a faster one for certain cases, it's nice to be able to have that backend like Cplex. But you know, it's sort of a trade-off here. I would love to be able to use all open source software, but unfortunately, these are very nice and they're kind of rooted in MATLAB, unfortunately. So, kind of trade-offs that you make. So one other thing. Oh, and if any of that was sort of gibberish, a lot of people don't worry about it. You'll learn sort of what all those things mean in solvers and SDPs and Cplex and all those kind of things. And if you have any questions, just come ask me about it. But essentially, what these things, the YAML and CVX being the good examples here, what they let you do is they let you write optimization problems in a very intuitive form. So here, we defined our variables theta as this SCP var, and that should be a k here, not an n. And then we called this function solve SDP. And solve SDP solves the optimization problem for us. The first parameter is the constraints for the problem, which we have none of here. We're just talking about a least squares function without constraints. And the second input is the objective function. And you'll notice here, I'm writing this out kind of just term by term. So I'm writing the phi times theta minus y, right? That was this thing here. Phi theta minus y. Squaring each element and taking the sum of those squared elements, which is just what we did with our 2 norm here. So I'm just writing solve this problem, where this is the objective function that we're trying to solve. It thinks for a while, returns theta. Theta is actually still one of these kind of specialized variables here, but then calling double theta gives you an actual real valued number. Double here is not anything about having 2 values. Double means double precision. So double theta tells you what it is in terms of real valued numbers. Now for least squares, this is sort of silly to do. You would never solve a least squares problem like this because it's much slower than just typing phi backslash y. But for other problems, this is much, much easier than trying to write out a optimization formulation of the problem, get it into the right form for a solver to parse, and then go solve it. At least for small size problems, because for big size it can get kind of slow. But for small size problems here, this is a much, much easier and more intuitive way of solving these problems. So we're going to use that extensively throughout this course and in the homeworks. I'm trying to see what time is. How much time do I have left? Okay, I have about 5 minutes left. So maybe I'll just offer a quick preview of the next class. And we'll cover this a little bit, but then we'll also get into nonlinear regression in the next class. And the issue here is, why did we use this least squares function? Right? I sort of just said, OK, we're going to pick some loss function, which should be big when things are far apart, small, 0 when they're equal. Why would we pick this prediction minus the true value squared. And you can come up with reasons for it, certainly. For those that know about this, if you have a probabilistic model, you can say that this function kind of corresponds to the log loss for a Gaussian likelihood function, for example. Again, don't worry about that if you haven't seen that before. So you can come up with justifications for this, certainly. But the truth is people use this even when these justifications are completely wrong. We still use it all the time. And the reason really is because it's easy to solve, I think. We use squared loss. I mean, it's sort of a weird choice, right? Why do we care about the squared difference of these two things? But the reason is, in some sense, because, well, we can write down the solution. It's phi backslash y. That's the solution. But we can pick other ones as well. If we want to be a little bit, do a little bit more work, let's pick some other ones. For example, let's pick the absolute loss, which is the absolute value difference of the absolute value of the difference between these two things. That might actually make more sense in a lot of cases, right? Because sometimes that might be what we actually care about optimizing. Maybe we want to say that there's some dead band, say epsilon. As long as they're within epsilon of each other, we don't care. We're going to say you've done as well as you can. You have zero loss as long as they're within epsilon, y hat and y. And after that, maybe there's either a squared error or an absolute error. All these things are possible, and in some sense, the one you want to actually pick will often depend on what you actually want to do with the predictions, right? If you are making predictions about energy consumption, as we are, and what you really care about in some sense is maybe your monetary loss or the loss in terms of emitting more carbon emissions than you would if you got this prediction better, so there may be some very complex loss that we really care about. And the choice of our actual application will dictate which loss we should use. But yet, despite that, and for reasons we'll get to next time, it is still very common to use kind of one of these types of loss functions like absolute loss or deadband loss. The tricky part with these things is that once we use a loss like this, we can no longer get an analytical solution like we did with least squares. These functions are not differentiable the way the least squares solution is, and so, or the way the squared error is, and so it's going to be very hard to solve analytically. Now, when I say very hard, I mean it'll be easy for us because we'll use these loss optimization libraries, but if you don't know how to do all that, it can be a lot harder. So next time, yeah?
Will be solved with the YALM?
Yeah, the YALM will solve these immediately, and we'll see that in lecture next time. In fact, this exact same program here, if you just change this to an absolute function, for example, in YALMIP, that would solve it. We'll go through how you used to solve it before YALMIP existed first, just to make it sort of even cooler that you can do that now, but you can solve it immediately with YALMIP. Yeah, that's what's kind of great about them, is that you can do this. Okay, so that'll be it for today. Are there any questions before we go? Okay. See you next week.